Hello，
于教授好。
你好，你好，
请问有听到我的声音吗？
可以。
好，那我们就稍待5分钟，9点准时开始。
好的。
好，谢谢教授。
于老师好。
魏老师你好。
就待会的话，就是我可能先帮你开个头，那后面就交给您帮大家这个分享一下。
OK，然后你是这个希望我用中文还是英文？
我看你好像还是比较习惯用英文，对吧？
英文好一些，不过中文也可以，看你这边需求，你觉得
没关系，
用这门
我们其实都可以的。
都可以是吧？那就用英文。
好的，没问题。
好的，我先 share 一下这个 screen。screen OK 吗？
可以的，可以。
OK， 好的。
感谢你。所以你们那边现在早上9点还是早上8点？
早上8点，早上10点。
感谢。
对，你这个对，这时间不好安排，这个你们也晚上。
对，那个庄启德老师的话是他习惯是晚上，所以我们这边的话就是早上。
OK。
是，那我想一定得要这样子，就是一边早一边晚，他逃不掉的。但是就是您上次跟我们建议，就是我们改成2个小时，我想这个确实帮助很大。
对，2个小时，对。
是，谢谢。
于教授好。于教授好。于教授，你的麦克风似乎是静音的。
哦，OK，对对
对，
对，不好
没有关系，
意思，
还没有开始。
现在 OK 吗？
OK，
好，
那个浩君待会再帮忙那个录影，让那个有一些跟不上的同学，他们可以再 review 一下。
好的，没有问题。
好，那我想时间差不多，我们就准时开始，好不好？那个，各位同仁、各位同学，大家晚上好。那个，我们学校就是高教生跟配合基体专业学程这边，很荣幸邀请到这个于世梦于老师来帮大家做这个线上的演讲。那，因为我们学校在推这个记忆体专业学程，校长他希望我们除了这个我们自己学校的老师以外，希望我们多邀请这个世界顶尖的学者跟大家一起做，不同的研究经验交流和分享。那我们自己因为有跟台大在合作一个 A 时代的记忆体晶片，记忆体内运算晶片设计的计划，那也是这样的一个机会认识了于世梦于老师。那我们发现，就是我们在这方面的研究，其实有非常多需要跟于老师来学习的地方，所以我们就趁前阵子他来台湾的时候，就特别邀请于老师，看能不能再帮我们安排几次的线上的演讲。那因为于老师他的这个研究非常的丰富啊，而且他年纪轻轻的就已经是 IEEE Fellow 了，所以他有非常多的这个研究，不管是今天讲的这个 RRAM 的部分，或者是未来会跟大家分享这个 FERAM，或者是这个 3D IC 的这个设计。那我想都非常值得同学和同仁大家可以一起来学习交流。那所以我们总共会有安排4次的演讲机会，那都是线上的。那因为我们双方有大概13个小时的时间差，于老师现在是一大早的时间，那我们这边是晚上的时间，所以安排这个演讲是非常不容易的，所以特别感谢于老师愿意给我们这样的一个 talk。那我就把剩下宝贵的时间交给于老师，谢谢。
谢谢魏老师的介绍。刚才魏老师也讲了，今天是第一次这个演讲，然后接下来4个礼拜每个礼拜都有一次，然后接下来的 topic 会是这个铁电 ferroelectric， 然后这个simulator neurosim， 然后最后一次是 3D IC。那我现在就开始今天的这个演讲，那我接下来用英文，然后有什么问题我们可以这个交流。这个我中间会停顿一些，这个给大家这个提问的这个时间。Okay, so let's get started with today's topic, computing memory with RRAM technology. This is the outline for today's presentation. So firstly, I will give a brief introduction about the AI hardware background, and then I will go through some basics for the RRAM device technology. And then I will talk a few prototype chip design with RRAM technology. The first one is a 90nm RRAM test vehicle that we designed and taped out with Wenbang from Taiwan. And we use this test vehicle for multi-level characterization and also the reliability characterization. And then we have 2 generations, 40nm RRAM and computing memory macro designed with TSMC. And the first macro will feature the security and robustness of the computing memory operation. And then the second macro is going to feature the ADC-free communication between subarrays. And then we will discuss some system-level design challenges with the RRAM computing memory macros, and then we will summarize this talk. So first of all, as you are very aware that the AI artificial intelligence applications today run on those hardware. And we have the computer vision and natural language processing applications are very popular today. And if you look at the computer platform, so here still the mainstream, I would say the NVIDIA GPU is still the workforce for the training of those large language model and other AI applications. And then we see that the ASIC design, for example, the Google's TPU is another trend that try to customize the hardware for those AI workloads. So here the TPU, or in general, the digital statistical array architecture is trying to do this near memory computing, where we have a lot of digital MAC units called PE for the same element, where we have the digital multiplier and adders to do the MAC multiply and accumulate operation. And then the data still come from the shared SRAM buffer on chip for both the input vector and also the neural network weights. So here we do the computation in the digital MAC PE and then save the intermediate data back to the shared SRAM buffer. So here we try to minimize the data movement because sometimes the partial result from one PE could be sent to the adjacent PE directly without going back to the shared SRAM. So here in the data flow, we try to minimize the data movement. And if you look at the energy efficiency for those platforms here in terms of the TOPS per watt, tera operations per second per watt. So essentially the throughput divided by power. So GPU is typically less than 1, and then those ASIC design is typically about 1 to 10 TOPS per watt. So here, when we talk about the TOPS per watt, we should refer to the precision of the computation. So here, typically, we normalize that to 8-bit by 8-bit MAC operation. So here, we face this memory warp problem because still we have to move the data around. So how about we just do the computation with the data? So this is the computing memory approach. So here, the idea is to have many of those computing memory, CRM macro, and each macro will have the memory array, and then we store the neural network weights into those memory array, and then only move the input and output data around. So we save at least the network weights movement in this case. So the computing memory approach could use the SRAM as the memory cell. And this could take advantage of the CMOS scaling because SRAM is available in today's advanced logic process. And the energy efficiency could be boosted to like 10 to 100 TOPS per watt. So like 1 order of magnitude higher. And also in this talk, we're going to discuss about the RRAM-based computing memory. So compared to the SRAM, RRAM is a non-volatile memory. So the good thing is that the weights could be stored in those RRAM after the chip is powered off. Therefore, this is good for the edge application because you can power down the chip and then you can still store the network model there. So this is a good way to do the edge inference. And then the next, beyond the RRAM, in the next lecture, next week, we're going to discuss about the very electric devices because we believe this is another technology breakthrough beyond the RRAM to do the computing memory. But today, let's just discuss RRAM first. So here are the basics for the computing memory. Essentially, this is a mixed signal compute. For example, if you have the neural network, then you have the input data. Input data will be mapped to the voltage that will be loaded in to the rows of the memory array or the word lengths to the memory array in parallel. And then the neural network weights will be mapped as the conductance of those memory cells. So then the voltage, input voltage multiplied by the conductance of the weights, then will result in a current. So we can sum up the current along the column or along the bitmap. Then at the end of the bitmap, we have this partial sum current represent the dot product between the input vector and the weight matrix. So here this is the end current. So we need to somehow convert to the digital through the ADC and to digital converter. And then, depending on the precision of the weights, we may need to do the further digital post-processing, for example, digital shift and add, to reconstruct the significance. And this is because, for example, if the memory cell, let's take SRAM, for example, is 1 bit data. But if your weight needs to be 8 bits, then you need 8 SRAM cells to represent 1 weight. Therefore, after you get 8 partial sum from those 8 columns, then you have to do the digital shift and add to reconstruct the 8-bit output. So this is the principle for the mixed signal compute. And of course, if the memory cell can store multi-bits, then this is more preferred. For example, if the memory cell can store 2 bits per cell, we only need 4 cells to represent the 8-bit weight. So in terms of the memory cell here, we have different implementations. For example, as I said, SRAM could be used. And typically, people would like to use 8 transistor SRAM as 1 bit weight. This is because we want to do the rate disturb free readout. So we add 2 additional rate transistor to the SRAM cell for the readout. And then if you want a more compact design, then we can change to this 1T1R, 1 transistor, 1 resistor, and this resistor could be RRAM, like what we are going to discuss today. And then the most compact implementation could be this 1 FEFET, ferroelectric field effector transistor. And we are going to discuss that in the next lecture, next week. So those are the possible implementations for the memory cell in this computing memory architecture. Okay, so in terms of the memory cell, we choose 1T1R. That R could be the R1. And also there are other candidates from the emerging non-volatile memory technology family. So here we could have R1, and most of the R1 is elementary. And we'll spend more details later to discuss about the R1 switching mechanism. But for now, the R1, most of the R1 today is based on this filament formation between 2 electrodes in the oxide. So the filament is made of oxygen vacancy. And then we could also have magnetic memory based on the MTJ, magnetic terminal junction. So depending on the ferromagnetic moment direction. So if they are in parallel direction, then you have higher tunneling current. If they are in anti-parallel configuration, you have lower tunneling current. So depending on the little magnet orientation, they could have different resistance. And also the phase changing memory is typically based on the chalcogenate material. And then the atoms will have either ordered crystalline phase or this random amorphous phase, depending on the programming condition. So if you have this amorphous phase, then the resistance will be higher. Or if you have this kind of ordered crystalline phase, the resistance will be lower. So then we can pass much current and then have the Joule fitting to locally melt this region to switch from the crystalline to the amorphous state. And therefore you can change the resistance. So this is the basics for the state changing memory. But no matter which memory, essentially there are 2 terminal resistors here. And we could have potentially multi-level resistance levels to represent the multi-bit weight. And then we also mentioned the FEFET. So this is a little bit different because here is a transistor structure. The difference is that the gate stack is replaced by the ferroelectric material, where you can have the spontaneous dipole inside the gate dielectric. So you can tune the threshold voltage depending on the dipole orientation. So here is a 3-terminal device. If the programming is through the gate and the readout is through the drain and the source. So this is a 3-terminal device, and the memory state will be implemented by different threshold voltage. So we'll discuss more about the FEFET in the next lecture. But here you can see that 1T1R, we could have different implementations. And today we are going to focus on the RRAM technology, because RRAM is available in Foundry's platform, and also RRAM could provide multi-level states in principle. Okay, so then next we will discuss some RRAM basics. So here, RRAM is short for resistive random access memory. And the key attributes and state of the art in terms of the key parameters are listed here. So the read and write speed could be less than 10 nanoseconds. Programming voltage about 1 to 3 volts. Programming current is about 1 to 100 microamp. And secondly, endurance, that means how many times you can write the data. It's generally larger than 10 to the power 6 cycles. The best reported number will be 10 to the power 12, but that was most of the foundry technology is around the 10 to the power 6. And retention, so at the elevated temperature, it's extrapolated to more than 10 years, and scalability less than 10 nanometer for the device itself. But this does not mean the entire 1T1R is less than 10 nanometer, because you still have the transistor that could be large. The reason is that even though the RRAM could be small, because you have to program in the RRAM with like 100 microamp, so your transistor needs to be large enough to provide this current. So the transistor size will limit the cell dimension. And then the material of the RRAM technology today was only hafnium oxide, and this is compatible with the CMOS technology. And then we use either the ALD or sputter to deposit the RRAM material, let's say 300 temperature. So this is compatible with the back-end line integration. Okay, so let's go through some history of the RRAM development. So this was back in 2008, when I just started RRAM research. So I read this paper from Yichi, Henyuan Li, my good friend. So his team at that time at Yichi, Taiwan, started working on the RRAM based on hafnium oxide. And here is a 1T1R implementation. The RRAM stack is shown here. So the key stack is based on the hafnium oxide with a buffer metal layer. So in this case, it's a titanium. And this titanium works as the oxygen scavenger. So basically, you take the oxygen from the hafnium oxide to the titanium. So titanium will be partially oxidized, and then you get the oxygen vacancy in the hafnium oxide. So this is how we get the oxygen vacancy in the oxide, because eventually we use the oxygen vacancy to form the filament for the RRAM switching, and then have the tinitride electrode. So let me show some data from this early demonstration. So here, this is a typical IV characteristic of RRAM. So here with the 1T1R, so essentially the transistor will provide a complex current to the RRAM switching. So initially the device is in high resistance state, so the current is low, and then as you ramp up the voltage, at a certain point, the device will set to the low resistance state, and the current will reach the complex current defined by the transistor. And then you switch back, and then you go to the other direction. And so on the negative voltage side, then at a certain point, the device will reset from the low resistance state back to the high resistance state. And then the current will drop. So you have this kind of butterfly switching behavior. So this is very typical RRAM characteristics. And you see that the set is kind of abrupt, and then the reset is kind of gradual. So you can repeat this switching on and off by many cycles. So in this graph, it shows the cycling endurance to 10 to the power 6 cycles, and we measure the resistance after each programming and each programming event, either the set with 1.5 volts amplitude pulse and reset with negative 1.4 volt pulse. So we measure the resistance. So you see that still after 1 million cycles, the resistance could be differentiable between high and low resistance stage. So that means the device is still alive. But of course, you see some degradation over the cycling and especially the hydrogen state keep decreasing. This is because with the cycling, you generate more and more oxygen and vacancy. So the device become more and more leaky. So here in this paper, it also demonstrates a faster switching speed. So for the set event, I believe here it shows that with 300 picosecond, you can switch it. Of course, this depends on the voltage you apply, but at least sub 1 nanosecond switching is possible in the RRAM device. And also here the retention means how long you can maintain the data. And here at baked temperature 150 degrees Celsius, the resistance can still maintain the window and extrapolate it to more than 10 years. But of course, this is not a good way to do the extrapolation because it's very hard to predict what will happen here after a few months. So the best way to do the extrapolation would be varying the temperature. So you get the 1/kT Arrhenius plot and then do the extrapolation. And then just fix the temperature to only one temperature. So you have to vary the temperature and then do see the failure and then do the extrapolation from there. But this is an early demonstration. So this is good at that time. And then here multi-level operations. So here basically you can have multi-level resistance by two ways. One is to partially reset by changing different reset voltage here. So you can have many levels. Or during the set operation, you can use a transistor to define different components current here. Then we can have different resistance level as well. So here we can have different resistance level and then measure their retention. So you see that in this case, those levels could be distinguished. But of course, as I said, so we should vary the temperature. This is only a fixed temperature. But at least for this 85 degrees C, up to here a few, I believe this is like a few hours, then we can have stable resistance. And then after a few years, IMEC from Europe, in Belgium, and also spent a lot of effort in the RRAM development. And again, they use hafnium oxide. The only difference compared to the E-trace implementation is that the stack here, the metal buffer layer changed from the titanium to hafnium. So here, but again, this hafnium will attract the oxygen from hafnium oxide. So here, this is the stack from the IMEC. And then they demonstrated a very small scale devices, 10 nanometer by 10 nanometer for the RRAM device. But of course, as I said, the transistor will be larger, but at least the RRAM device is 10 nanometer by 10 nanometer in this case. So IMEC team reported some interesting behavior from the RRAM. For example, here the voltage of the forming, which is the first time programming. The voltage depends on the area of the device. If we scale down the device, the voltage actually goes up. This is because you have less defects in less dimensions. Therefore, you may need higher voltage to trigger the switching. And also the switching voltage depends on the hafnium cap, that buffer layer thickness. If you have higher thickness of hafnium metal, you extract more oxygen from the hafnium oxide, so you are going to lower down the forming voltage. And also here, the IMEC team reported the scaling trend for the set and reset voltages. We do not see too much dependence over the devices from 1 micrometer square to 10 nanometer by 10 nanometer square. So the switching voltage is pretty the same for both set and reset. This also suggests this is a fundamental switching. And also here the on-state and off-state current does not really change too much over different sizes. So that means the filament is pretty small, like maybe 10 by 10 nanometer in that dimension. Even though your device may be micrometer square, your filament which means the active switching region is pretty small. And also here there is a dependency between the switching time and then the voltage you apply. So here you say for different switching time, for example, 10 to the power -6, that's 1 microsecond. So here 10 to the -8, 10 nanosecond. If you want to speed up the operation, you have to raise the voltage. That means higher voltage, you can switch faster. So here also for the reset, you see that if you want to switch within like 10 nanoseconds, then you have to apply like more than 2.5 volt or even close to 3 volts for less than 10 nanosecond operation. So the speed depends on the voltage you apply. And also the cycling endurance as measured by IMEC. So here it has different failure modes. So depending on the set and reset pulse condition, sometimes you see that after 1 million cycles, then the low resistance state will become high resistance state eventually. This is because in this condition, the set condition, RRAM voltage 0.9 volt is kind of weak. So you do not have strong enough set condition. So most of the failure mode will be stuck in the high resistance stage. But if you further increase the RRAM voltage for the set condition, for example, the last case 1.4 volts, and then the set is too strong, then you see that after 1 million cycles, the high resistance state will become low resistance state, will stuck at the low resistance state because the set is too strong. So the key here is to balance the set and reset condition. So here, after optimizing those programming conditions, so here you see that IMEC demonstrated in the power 10 switching cycles, still we have a memory window between high and low resistance stage. This is with the optimal condition. So the RRAM is very sensitive to your programming condition. And also here, this is a retention measurement. So this is what I mentioned earlier. This is a better way to do the retention. You have to change the temperature. So here at a single temperature 200 C, then you, for example, look at the low resistance state over time. So you see the resistance goes up. You set a failure criterion, and then you record the time here. So then you mark this as a failing time to failure point. So you record this for 200 C, and then you change the temperature to 250 or 150. You see that the result current will have different rates of the failure. So you can record the time to failure at different temperature. Therefore, you get 3 temperature, you get 3 time to failure points. And here you see that you have 3 points, and then with 3 different temperature, you have to convert the temperature to 1/KT scale. So you have to change the degree Celsius to Kelvin, and then back to the KT, and then change the unit to electron volts. And then you look at the time to failure. So then by extrapolation, and because this will be in high temperature, this will be 250 C, this is 200 C, this is 150 C. So you do the extrapolation because this is a 1/KT Arrhenius relationship. So then you trap that to the 10-year which is 3 times 10 to the power 8 seconds. And then you look at this temperature. So in those 2 cases, depending on the low resistance state, without current, the compliance current level. For example, if it's your transistor compliance is 100 micron, then here in this case, by extrapolation, and the device should sustain the retention for 10 years at 105 degrees Celsius. If you change the compliance current to 10 micron, then the device will sustain only up to 92 degrees. So this is a better way to do the retention and extrapolation. You have to vary the temperature. And then after another few years, the RRAM become available. from the industry platform. So as you know, ITRI and IMEC are research institutes, so they do early stage, development. But eventually, for production, we have to switch to the major foundry companies like TSMC. So TSMC has been working on RRAM for many years, and this is one of the early reports from TSMC. This is at ICC 2018 for a 40 nanometer RRAM macro. So here the cycling data. So in this case, only 1,000 cycles reported, and at different temperatures. So they pass the temperature from negative 40 to positive 125 degrees C. And here are some more parameters. So the technology node 40 nanometer and cell size 53 F square. F is about 40 nanometer. And then this is one macro with 256 kilobits. And then the time, access time is about 9 nanoseconds. So this is the initial demonstration from TSMC. And after that, I believe TSMC has continued the development of RRAM to 28 nanometer and also 22 nanometer. So at 3 nodes, 40, 28, and 22, TSMC is offering the RRAM process. And this is based on hafnium oxide, even though the details are not disclosed what kind of stack, but we all know this is hafnium oxide. And also Intel reported 22 nanometer RRAM on their 22 nanometer FinFET platform. I think recently they renamed this to be Intel 16 nanometer. So they call Intel 22 FFL at that time. So here, this is also hafnium oxide RRAM. And then the density is about 10 megabit per millimeter square for the entire macro. And then the write time is kind of slow, less than 10 microseconds. And also for TSMC, the write time is not like 10 nanoseconds. Write time is probably hundreds of nanoseconds. And then the read time is fast, a few nanoseconds. So you see that write is much slower than the read. And then the energy per bit is like 1 picojoule, and measured bit error rate is less than 10 to the power minus 5. So here, this is cross-sectional view for the integration. So here, this is RRAM stack on top of the transistor. So here you see the FinFET on the bottom, and then at the drain up here, we have the RRAM. So here, this is the layout for the Intel's RRAM implementation. So as I said, so even the RRAM itself could be smaller, but then the entire 1T1R layout is like this size, 200 nanometer by 200 nanometer. I would say in TSMC also has similar dimension. So here, this RRAM is integrated at metal 4. You see that here, transistor down to here, and metal 1, 2, 3, 4. So here, roughly at metal 4, we have the RRAM. So this is a 2-fin, and then, sorry, this is actually 4-fin to drive one RRAM cell. This is closer look at RRAM. So here, the metal, this is the metal 126, and the metal 7 and the metal 8 are top global interconnects for power and other power, most of the power delivery. But here for the signaling is down here. So here, if you zoom in, this is RRAM, and from the previous slide. So here, metal 4, you have the RRAM. And yeah, this is again larger view of the RRAM cell. So we don't know the material exactly, but we suspect it's hafnium oxide. Okay. Okay, so here is a quick summary for the RRAM chip reported in the previous years. As I said, in TSMC 40, Intel 22, and TSMC also reported 22. So it's all 1T1R. and then the cell size is like 50 to 100 f squared, and then the on-state resistance is about a few kilo ohm, and the on-off ratio, that means R off divided by R on, is like 5 to 10, I would say 5 to 10. And then the red voltage, like 1.5 to 3 volts roughly. And then the red pulse, like 1 microsecond or 2 microsecond, much slower than read. Read could be less than 10 nanosecond, as you see here. And the endurance, 1,000 cycle to 100 to 10,000 cycle in that range. So you see that this is at array level. This is not a single device. You see earlier what we reported from E-Train or IMAC. Those measurements are done at single device level. So here the data recorded by those ISCC or VLSI papers are at the array level. So here this means an array level performance. That means the worst bit in the array will be in those range. So of course this is lower than a single device that could be better than the worst case bit in the array. So but here anyway, this is the state of the art for the RRAM chip demonstration. Okay, so the next I will talk about some of our research in this field. And first I will discuss the 90 nanometer RRAM test vehicle. So this is in collaboration with Wenbang, Huabang. So I have a good friend at Wenbang, Brett Chang. He helped us to get access to Wenbang's RRAM and technology at 90 nanometer. Again, this is 1T1R with graphene oxide. And so we designed this 256 by 256 RRAM array for the testing purpose. And there are some peripheral circuits like decoder level shifter to help with the programming. So here, what we want to do is to look at the multi-level operation from this test chip. So we emphasize on the computing memory application. So the requirement for the multi-level operation actually is different from the multi-level storage. So the reason is that here for the multi-level storage, you see that as long as we have different readout current, then here we have the gap between adjacent level, then we could differentiate different bits. So the criterion is that we need to enlarge the gap between the tail bits for those two adjacent distribution. So as long as we have this gap, then we are good. But for the multi-level RRAM in the computing memory application, then this is a different requirement. So not only we need to enlarge this gap, but also for one distribution, we have to minimize the standard deviation for the distribution. The reason is that we later add up the current for individual cell. So each cell, if you deviate from the center, you will accumulate the error. So we need to tighten the distribution, not only kill the tail bits, but also make this distribution tight around the center. So this is much more difficult than just killing the tail bits. That means mostly we have to make sure all the cells close to the meeting value. So this is much more difficult. So here, anyway, so we use this test vehicle and then develop the write and verify protocol to tighten the distribution. So this must be verified because after a single probing pulse, then it's very difficult to achieve the target. So here, I will skip the details of the protocol, but basically it's a program to define the optimal set and reset pulse condition, and depending on the write and verify protocol. So here I will just use this this figure to illustrate the idea. Very straightforward. For example, here you start with current state, the conductance is low, and then if this is our target level, so we apply first set pulses, and then the conductance will gradually approach this region, but sometimes it will overshoot. So after overshoot, we may have to reset the device, bring the resistance back, and then do the set again. So after tens of pulses, finally, we can reach this target range. So this is so-called write and verify. First write, you write the conductance may not be in your target, and then you verify it. So eventually you converge to the target level. So you need like to 30 pulses to do this. So here, after this write and verify at array level, so here we tested, I think a few kilobits. So each level is like a few kilobits. So here you see that we managed to have 8 levels, and each level is close to the center of the distribution. So here, this is in the log scale. So here, those are really the tail. Most of the devices in the center. So here, if you measure the sigma, so the sigma of each distribution is less than 1.5% for those 8 levels. So this is not easy, but we managed to do this by this aggressive write and verify technique. So here, more data to show the distribution after the verify. So here, this is another, this is CDF, cumulative density function. So here, this is the dashed line is a target. So here, for those 8 levels, for example, we need to define a lower bound and higher bound for the conductance range. And then after the, so here, n equals to 1, that means only one verify cycle. So you see that this tail is still large. Most of the cells are not within this conductance range. But after 30 verify cycles, you see that the green line, most of the cells are within this range. Only 1% cells are outside the range. So this is how we read the data. So here we can repeat this for all the levels. So we define the median value of the conductance. For example, here the highest conductance level is 156 microsiemens, and the second one is 133 and 110. So this is to uniformly set the conductance into 8 levels. So this is the way we define 3-bit data. Okay, so then after the programming, then we care about the stability of those multi-level states. And here we measure the retention under the stress, under different temperature. So here you see that this is for 4 levels. And right after the programming, we can tighten it. So most of the cells you see are within this target. But as the time goes by, so just leave the device there. You just leave the chip without touching it. So then after some time, you see the distribution start to relax. So here you have more tail bits after 100 hours. So you do nothing to the chip, but the chip just stays there. And then if you remeasure it, then you will get more tail bits. So that we call this relaxation behavior. So after initial programming, you can tighten the distribution, but after some time, the distribution tends to spread out. So we also say that in the intermediate state, here the state 1 and 2, this is the most vulnerable to this one. It's most vulnerable. We call state 2. It's most vulnerable to this effect because in this case, this has a very weak filament, so it's very easy to be disturbed. And if we measure the state 2, then at different temperature, then you see that at higher temperature, it will drift faster. And also the sigma of that distribution will increase at higher temperature. So this means that this state 2 is not very stable because it has a weak filament in that case. And also under stress, so here if we apply voltage, keep a constant voltage on the bit line, then this will further accelerate the drift of the resistance. At higher bit line voltage, it will drift faster. So this means that the device may suffer from this relaxation and the greater stress behavior. So of course, with the stress, then you will speed up the degradation. But even without stress, then the device will relax by itself. So this will impose more challenges for the computing memory chip reliability, because you want the chip to be, functional all the time. But as time goes by, then you will have some reliability problems. So then here we propose some mitigation scheme to combat for this relaxation effects. So here, first for the relaxation, we see that as time goes by, the resistance or conductance will drift, but eventually it will saturate. So that means we need to wait 100 hours before we fine-tune the reference voltage for the sense amp or for the ADC. So we do not rely on the initial state. Let's say after the initial programming, we just wait for 100 hours for the chip to relax. And after that, we set the reference voltage for the sense amplifier, so we can read the output more stably after 100 hours. And then the other idea is to play some trick in the algorithm for the neural network training. So during the training, we're going to define the algorithm weights, and then we can add some penalty to the intermediate state weights. So as a result, after the training, we will get more cells in either the lowest or highest conductance or weights, and we get less weights in the middle. So this could help because we have less number of the bits that are vulnerable. So then we can get better accuracy. So here we did some neural network simulation. So here, for example, if we push the weights away from the middle, let's say here only 10% in the middle states and 40% on the high and the low states, then we can still achieve good baseline. And then we can have more stable behavior after the hours, hundreds of hours, because here we have less weights that are vulnerable. Also for the temperature instability, as we bake the device, then we get more drift of the weights. So here we have some other algorithm technique, so-called the noise aware training and the batch norm adaptation for different temperatures. So the idea is that we inject the behavior of the drift into the training process. So it's like we add some noise to the training. So therefore, the neural network could be more robust to the drift of the weights after the training is done. And also we can fine-tune the batch norm parameter at different temperature to adjust the batch norm operation for different temperature. Of course, this assumes that on chip there is a temperature sensor. You can predict the temperature. Therefore, you can adjust the batch norm parameters at those register. Then you can deal with the temperature change more reliably. So those are some algorithm and chip design ideas to further mitigate the effects. All right, so this is for the multi-level operation. So here, should I stop for a few minutes? If there's any question, feel free. So any questions from the audience here? As you can see, it's not easy to make this work at array level, at chip level. So. All right, so then we can continue. So I will talk about the 40 nanometer RRAM design with TSMC. So before that, there are quite a few prior arts in the literature. People have demonstrated RRAM-based computing memory macro, and many of the contributions come from Professor Marvin Chang's group, Zhang Mengfan 老师, from National Tsinghua University, and he has the RRAM access from TSMC as well. So here then let's summarize the design challenges in the RRAM-based computing memory. And we already addressed some of the challenges in the previous demonstration with the Win-bounds test vehicle. So the RRAM on-off ratio is not that large. So here, if you look at the summary from Intel and TSMC the table, the RRAM on-off ratio is less than 10. And so this is tricky because 10 on cells, 10 off cells will be equivalent to 1 on cell if on-off ratio is only 10. So you enable 10 rows, and if those 10 rows have all off state, then you have 10 off current. This is equivalent to 1 row that is with on current. So if the on-off ratio is not large enough, we cannot turn on many rows. And then second, we have the security issue because you store the memory weights and you store the neural network weights on the memory. So if someone read out all the memory data, then he or she could reverse engineer the network model, which is valuable because the neural network model, the companies spend like hours, not hours, I mean even days or weeks to train the model. And then with the GPU, clusters of GPU and then private data and train the model. And then you deploy the model to the inference chip, store in the memory. And if someone read out all the memory data, then he or she could just reverse engineer the model. So then there are some other challenges. For example, this is mixed signal design. Therefore, it will suffer from the PVT process voltage temperature variation. So here, especially the sense amplifier here will suffer from that. And if you lower the VDD, then the sense margin is even lower. So we'll have a lot of errors coming from the peripheral circuits. And also the programming is very slow, as I showed earlier in the testing protocol. If we use off-chip instrument to verify individual cells, it will take forever to verify the entire chip. And also here, we have the challenges due to the ADC quantization loss, and then the ADC precision needs to be high to maintain the accuracy. So those will impose many challenges in the ADC design. So here then in our design tapeout, we try to address some of those challenges in this slide. So the first generation RRAM computing memory macro designed with TSMC. So here again, I have very good relationship with TSMC, and then they tenderly support us by offering us the PDK for the RRAM process, and then help us to do the integration. But anyway, so here the design is divided into 2 parts. So here you see this orange blocks, the analog blocks. Mostly will need the manual design layout. So we have the array and then the marks, and then the level shifter for word line input, and level shifter for the bit line input, output, and then the sense amp, and then the ADC. So we need those manual design. And then for the timing and input output control, and then the encoder and shift and add, and the scan in, scan out. So those are digital blocks. So those could be written in, Verilog and RTL format, and then do the synthesis, placement and route, and then those could be the digital flow. And here we have some techniques to address those design challenges. I will discuss that one by one in the next few slides. So first, for the input sparsity control, so we try to skip some of the operations, because if the input vector has 0, then that will not contribute to the output. So we want to skip enabling that rule. So first, we will do a scan of the input vector, and then we will have a counter to accumulate 7 ones, and then we will turn those 7 rows in parallel instead of those rows with 0, with skip that row. So this will enable better energy efficiency, because we don't need to operate on those useless rows. So depending on the input sparsity, then we can, if the input sparsity is high, which is typically true for most of the neural network, like 60–80%, then we can boost the energy efficiency and also compute efficiency. So here the design is to accumulate 7 rows that are in one, and then turn on those 7 rows in parallel. And after that, then we will have this preferred circuits to digitize those 7 rows. So here we have the max, because the ADC will take some space, so I have to share the ADC among 8 columns. And then once we select the corresponding column, then the bitline voltage here, or let's say the bitline current, will be converted to the bitline voltage by this pull-up PMOS transistor. So essentially there's a pull-down network by the RRAM cells here, and then there's a pull-up PMOS. So the relative strength of the pull-down RRAM network versus the pull-up PMOS will determine the bitline voltage here. If you have more cells in on state in the RRAM cells, then you have stronger pull-down. Therefore, the bitline voltage will be lower. Then this analog bitline voltage will be sensed by the 3-bit flash ADC. That means 7 sense amplifiers, voltage mode sense amplifiers. And then we will encode that into a 3-bit output data by the flash ADC thermometer coding. So here, then the security, as I mentioned earlier, so we want to protect the data stored in the RRAM array. So one simple idea is to encode the data by a very simple XOR cipher. So basically, we need to use XOR operation. So here the data is implemented by a pair of those 1T1R. So as a pair implement one real data. Then we have the real data and the real data bar. So then we need to decrypt the data when we do the operation. So we need the key. But we do not apply the key to the data. We apply the key to the input. Therefore, here we have the AND gate to select which row to turn on. So only with the correct key, we will turn on the correct row. So it's XOR operation. If you have a negative key, then you should turn on the key bar, and then you have the weight bar. So key bar and weight bar, then you still get the correct output. So here then, of course, we will have the overhead, because here we need to have a pair of the a cell to represent one weight. Previously, only one T1R. Now we need 2 T2R. So it's an overhead in terms of the memory capacity. So here, then we try to encrypt only part of the network, because we don't want to encrypt the entire network. Otherwise, we want to double the memory capacity. So we only want to encrypt a single layer of the network. So here in this algorithm simulation, we encrypt one layer of this VGG8 network for CIFAR10 dataset. Then turns out we only need to encrypt any one of this layer. Then under the random guess attack, then the attack accuracy, that means the adversary to read out the data, with very low accuracy. So this is good for us. So this is just to encrypt a single layer. But for other network, for example, here ResNet 34, if you only encrypt certain layer, for example, here the 22 layer, the 22 snare, then the adversary could still get good accuracy output. This is because the ResNet has some bypass feature. So you encrypt only a single layer may not prevent the bypass of the information. So here we have to encrypt multiple layers, for example, layer 2 and layer 5. Then under the accuracy, under attack, the accuracy could be low, but here you have to encrypt the total width like 74 kilobits. So here is an overhead. Depending on the accuracy you need to prevent from the attack, then you may encrypt more layers. And here then let's talk about the on-chip read and verify, because here we want to have the read and verify protocol, as I mentioned earlier. In the Wenbang chip, we use the instrument to do the verify. But here, to speed up, we have to have on-chip controller to do the read and verify instead of using the off-chip equipment. So here, we need to have a dual mode sense app to set the higher and lower boundary of the RRAM resistance. So then here we will just implement the protocol similar to what we showed earlier, but have all of them on chip. So here those two sense apps will define a window for the sensing to pass. So here we can define the window as 200 ohm or 400 ohm. So then you see that we want most of the cells will pass within this window, because again, we need to tighten the distribution to the center. And this is for the low state. For the high state, we want most of the cell to pass this boundary. So then we use the sensor to basically label if the output is passing or if the output fail. So here, this is a simplified protocol. Again, we have to do this read and verify, very similar as before. So for the set condition, they want to reach this target, which is defined by those two sense amps, the higher boundary and lower boundary. So then if we are lucky, then after a few cycles of the set pulse, we end up here, then we are good, we stop the programming. But if somehow we are unlucky, then we overshoot, then we have to bring it back and then redo it. And eventually we end up here. So this is fully implemented on chip with the sense amp. This is different from the Wenbang chip where we have the equipment to do this job, but now it's fully on chip. So this is another example for tighten the low high state, which just keep increasing above this resistance. Then we are good. So here you see that after the programming and the verify. So initially, then this is this initial distribution. Initially is a black distribution, but after the verify, then we try to tighten the distribution, make most of the tails into this window. So this is for the low state. And for the high state, without verifying, then initially we have many of the cell will fail below this boundary line. But after the verify, we push most of the cells above this boundary. So in this case, we try to target the on-off ratio 7, because here we turn on 7 rows in parallel. So we have to make sure the on-off ratio is larger than 7. So here, this is much faster than we do this one by one off chip. So we could have 10 power 5 times programming speed up on chip compared using the off chip external test equipment. And also here we have challenges in the ADC reference design at different temperature. This is because its RRAM resistance will change at higher temperature. So here, this is a measured bitline voltage at different temperature. So at 25 degrees C, then we have this blue curve. But if we measure the chip at 120 degree, then we measure this bitline voltage. And then the bitline voltage will change like this, depending on how many cells are in the on state. So here, ADC partial sum means you have 1 RRAM cell in the on state or 2 RRAM cell in the on state. So we have to define the ADC reference here to read out 7 levels correctly. But if we define those, here, this dash 9 are the reference voltages for the 7 sense amplifier. But if we define this reference at 25 degrees C, you see that at higher degrees C, then we will miss some code. Like the output 6 and 7 will be wrong. Because here, if a reference does not change, but the beta voltage change, then we will get the error, basically. So we have to address this challenge. The idea is also simple. We can have some dummy columns with also RRAM cells, but we program them into this kind of pattern to generate the reference voltages with those RRAM cells. So that means we do not use an external voltage reference generator. We use on-chip RRAM to generate the reference. So this could provide self-tracking to the temperature because those dummy RRAM cells will also drift similarly as the real data column. So then we can move together. Therefore, we can compensate the change of the references to some extent. So here, with this idea, then we measure the ADC output. And here, this is the percentage of the correct readout. So here with the external reference, you see that here is almost 0% at high temperature, 120 degrees. But with the on-chip reference, we can recover many of those readouts. But still, you see the reference with on-chip reference, still the accuracy is not 100% at high temperature due to noise and other process variation. So here, but at least we can recover some of the accuracy loss at high temperature. So with this kind of statistics, we run this neural network simulation for the C-pattern data set. And then you see that here at 25 degrees C, then we have close to the software baseline of 92% accuracy. But with the external reference at 120 degrees C, the accuracy dropped to like only 80%. And then with this on-chip reference, we can recover to 86%. But of course, this is still not ideal. We still have some errors due to thermal noise and other non-ideal effects at higher temperature. So that means we need to further protect the data and beyond this ADC references. So the idea is to use error correction. And also, when we reduce the voltage VDD, then we will have less sense margin. You see here, this is again the beta voltage as a function of the ADC output. So here at lower VDD, then we have less margin. The total dynamic range is less. So this is more vulnerable to the noise. So at higher temperature and lower VDD, will need to protect the output data. So the idea is ECC, error correction code. So here, error correction is not new. I mean, for the memory array, all the memory array will have ECC. But here, the challenge is that we do this parallel computation. So this is incompatible with the conventional ECC because conventional ECC, you're going to add some parity bits and then protect these data bits, but it's in row by row fashion. You only turn on one row. But here, if you turn on multiple rows, you cannot use conventional ECC. So here we propose this MAC ECC scheme, and I will skip the algebra here. And then the key idea is that we add those parity bits together. So here the goal is not to protect the individual bits, but we protect the partial sum computational results. So even those bits could be wrong, but as long as here the output is correct, then we are good. So we do not protect individual bits. We add a group of these parity bits to protect the partial sum, the MAC ECC MAC results. So this is the whole idea behind this scheme. So here that means we need to add some additional logic to do this decoding, and then we can recover the errors for the output. So this is the main idea. And now to implement this MAC ECC, we need to add some additional modules. but the parity bits are encoded off chip. So depending on the data pattern, and then you know what to provide and what to encode to the parity bits. So this could be predefined. But during the runtime, we are going to read out the partial sum, the MAC results, and also the results from the dummy columns, the parity bits, and then we will do some calculation there to calculate the so-called syndrome. So here, I will skip the details, but to do that, we have to have a few blocks to do the computation after the ADC output, which is the raw data. Then we need to do the multiplier, modular, decode, comparator. We have to do something to detect whether there's error or not. If there's an error, then we will correct that error. But here there's a limitation for how many errors we can correct. So in this case, we can only correct one error out of one row. So if you have more errors, then this is beyond the capability. So here we also try to examine which bit to protect. As you can imagine, so if you have errors to the MSB, most significant bits, you will have more accuracy degradation for the neural network. So here we only protect the MSB. So if you do not protect, this is the accuracy drop with the bit error rate. But if you protect the MSB, then you can recover the accuracy drop from here to here to the red one. This is when you only protect the MSB. But if you protect all the bits, then you can have almost the perfect accuracy. So here, of course, protection will have come with the overhead. So we try to only protect the MSB if possible. So with only MSB, then we can reduce the bit error rate. For example, here reduce the bit error rate more than 10 times. If the bit error, raw bit error rate is like 0.1%, then after the BCC, we can enhance or let's say reduce the bit error rate by 10 times. So here you see this number is like 13.8. This is 13 means the 13 data bits. 8 means 8 parity bits. So this is overhead. This is the penalty you have to pay for. If you want to protect the 13 bits, you have to add additional 8 bits. So it's expensive. So that's why we only want to protect the MSB with this scheme. So here, this is the measurement result. After we apply the ECC, you see that for the large partial sum, in this case, after we reduce the voltage to 0.7 volts, then you see that we can recover many of those errors, but still it's not perfect. But with this recovery, it's good enough to maintain the software accuracy. So here, again, we run the neural network model with this kind of statistics from the measurement. So here you see that after the ECC, and let's say 16 bits, we use 10 bits to protect 16 bits. Then at this low VDD, we can still maintain almost to the software baseline. So this provides some opportunities to do the DVFS, dynamic voltage frequency scaling. So here we can run the chip at different VDD. Of course, at lower VDD, then the frequency will be lower, but the energy efficiency will be better. As you know, when you run at lower VDD, and then generally for the chip, you have better efficiency. So this is the idea of the DVFS, dynamic voltage frequency scaling. So then with this ECC scheme, we can ensure that at no VDD, the output is still accurate. So here, of course, we have to pay for some overhead for the ECC scheme. But here we can enable the ultra low VDD operation because at 40 nanometers, the nominal VDD is 1 volt. But here we can operate the chip at 0.7 volts and still get a reliable output. So this is the idea for this first generation RRAM chip. And then next, we'll discuss the second generation RRAM chip. So realize some of the challenges associated with the ADC. So here, then we'll try to get rid of the ADC. So the ADC, as you know, will have quantization loss. If you do not have high precision ADC, then if you only have 3-bit ADC, then accuracy will drop. If you enable too many rows, 256 by 256 array, then you need high precision ADC. And then here also ADC will introduce the area and the energy overhead. So we have to really carefully design the ADC. So why not we get rid of the ADC? So this is the idea behind the second generation design. So we want to get rid of the ADC. So then here we want to use this pulse width modulation as the input encoding scheme. So we do not represent the data in the digital bits. We represent the data in a pulse. But this pulse width will represent the data. If you have a longer width, then your data is larger. So then we could use this pulse width modulation, and then the output ADC is replaced by the edge capacitor. So we have some capacitor to store the charges, and then we have an analog voltage on the capacitor to represent the output. So we do not convert the data to the digital domain. We still maintain the output as analog voltage. So here to demonstrate this idea, we designed two array, and each array is 256 by 256 RRAM array. So we have more analog blocks in this case, because here we have the current voltage converter, and after that we have the edge cap to store the voltage. So here I will show you the data flow. So input is still like digital data, but then after the compute, you get the analog data. Analog data, as I said, stored on the cap. So you have analog voltage. So the key here is to convert the analog voltage through this ramp generator to the input that is for the next array. But this input will be converted to the pulse with different widths. So here, if you have a larger voltage, you will have longer pulse. But the pulse, all those pulses have the same amplitude. So here the data is encoded from the voltage to the pulse width. And then we can do the computation again. And then after that, we will get another voltage, analog voltage. So you say the input to the array is a pulse width modulated signal, and the output from the array will be the analog voltage. There's no explicit ADC in this design. Okay, so here we will show more details in the design. So here, I think the key block is this current to voltage and ramp generation. So here, again, we have this RRAM array, and then end of the bit line, after the max, we used to have ADC, but now we have this kind of a circuit. So here, essentially, you see that this bit line, we have two branches, and then we will have the positive weights and negative weights. And so here we have the positive current and negative current. And then here, essentially through the current mirror to this branch, this will be the subtraction between the positive current and negative current. So here the P3, here we have the current represents the results that could also deal with the positive and negative weights. And then we need to downsize the current, because here we have to charge up the cap. Sometimes the current is too large. So through the current mirror, by sizing the transistor, you can downsize the current. So this current will eventually charge up this cap. So depending on the current amplitude, you will have different analog voltages here. And then here, there are some control switch to charge and then transfer the charge out. Then here we have the ramp generator to generate a ramp signal. And then this analog voltage and the ramp signal will be compared. And then that will generate, after the comparator, then we generate the rectangle pulse with pulse width that is proportional to the analog voltage when you compare to the ramp signal. So this is how it operates. So here are more details. As I said, so here we have to downsize the current. And then here for the cap, we store the charges, voltages on the cap. So here are the timing waveform for the computation. So here for input vector, we will have different pulse widths. And then after that, we will get the positive current, negative current, and the difference will be transferred as an I charge here. And I charge is going to charge up the cap here. So this, and then eventually you will reach to some analog voltage. So in the next phase, this analog voltage will stay there, but now with this yellow voltage, which is a ramp signal from the ramp generator. This is a ramp generator circuit to generate this ramp with certain slope. So we are going to ramp up the yellow voltage and then compare to the green voltage, which is the computational result from the previous array. So you will compare these two voltage. So here the green voltage will stay there, and then you have the ramp voltage goes up. So when they meet, then it will trigger the flip of the comparator. So you can get the boiling edge of the pulse output. So you see that depending on the, because the ramp slope is constant. So if you have, let's say the dash line here, the lower voltage, then you get a shorter pulse here. If you have the solid line, then you will wait for longer, then you get a larger pulse. So this is how we generate the pulse width modulated signal to the next array. So with this scheme, this is the setup for the measurement, and here we experimentally demonstrated the pulse width is modulated by the MAC value. So here, this is an example of the waveform measured from the test chip. And of course, due to the variation and noises, it's not always perfect. So depending on the ideal MAC value, then the measurement, the output from the pulse width modulation signal may have some variation along this line. So here we have to consider this kind of variation. So here we first we simulated with temporal noise, and also measured with the noise, measured with the chip, and also consider the different columns. Then we have the spatial variation. So let's say the deviation from the dash line by the measurement is like 4% deviation from the dash line. So we are going to inject this 4% error to the neural network model to see the impact of the accuracy. So here, this is different kinds of neural network model by the injection of the pulse width modulation signal. So basically, the pulse width will have some variation. So that means your input data is not accurate. But even with this 4%, we can see that there are some degradation for those data sets baseline accuracy, but still is manageable in to some extent. But of course, this is not ideal. We still need to develop better protection, like error correction, other mechanism. But error correction is tricky here because we don't have the digital bits. But anyway, so here we have demonstrated that with this pulse width modulation signal, we can still do some computation with minimal degradation. But as you can see, the accuracy is not perfect with all those chips demonstrations so far. So no one achieved the best, the baseline accuracy as a software. So more or less, we will suffer from the accuracy degradation. So that's a key challenge in this computing memory architecture, because we have the mixed signal analog computation, which is vulnerable to the noise and the variations. But anyway, so compared to the first generation chip, the second generation chip, because we get rid of the ADC, so we save the area by 50% and also boost the throughput energy efficiency significantly compared to the first generation chip. This is because we use this pulse width modulation to represent high precision input and output data without going through the digital chip NAD for the high precision. So this is the benefits of this second generation chip. And then we compare to other earlier demonstrations in the literature. And also we have quite competitive energy efficiency and normalized to the same precision. So we have pretty competitive precision, even though we have an older technology load. So this is a summary of the second generation chip. I will skip the details. We have two sub-arrays, in total 128 kilobit RRAM. And then we have like 1 to 4% accuracy drop due to the noise and variation. But we have a very high energy efficiency compared to the previous reports. All right, so then we'll continue and to have some discussions on the challenges we see so far and I will have some outlook on the summary. So here, this is a quick summary for the RRAM-based computing memory. As you can see in our prior practice and also the efforts from other research groups. So the 1T1R, 1R, or 2T2R can be used. And then the cell size could be 30F² to 60F², which is about 2 times to 5 times higher density than the SRAM at the same technology node. I have to emphasize at the same technology node. This is because SRAM could be available at today's 3 nanometer node, but RRAM, the best you can have is 22 nanometer from either TSMC or Intel, as I said. So you cannot compare the RRAM, 22 nanometer RRAM with 3 nanometer SRAM, so then that will be unfair. But at the same technology node, if you compare RRAM, 22 nanometer RRAM compared to 22 nanometer SRAM, then you have some density improvement. So RRAM could be programmed multi-level, but we have to do it very carefully because we need to address the relaxation, drift, stress, retention, and high temperature. You see that we have done a lot of factorization, and so it's not easy to make those multi-level operation reliably. And also RRAM still faces the challenge of high programming voltage. And so here the programming voltage for the first time could be like 3 volts. So this is pretty high compared to the logic VDD, which is only 1 volt or below. So we need the high voltage generation on chip. And then this will bring the overhead in the charge pump and the level shifter in the design. And also RRAM's low resistance state, low on-state resistance is still pretty low, a few kilo ohm. So that means each RRAM will give you like 10 micron when you read out. If you turn on multiple rows, usually you will get like hundreds of micron or even million current from the bitmap. So this current is too large for the preferred circuits to manage. If you read out only one cell, it's fine. But if you turn on multiple rows to read out in parallel, then this current is too high. And we also demonstrated the record verify, which is essential for programming the resistance, pattern the distribution. We can do it for the inference because we can, spend some time in just once to verify the resistance. But this will be difficult for in-situ training because it's never smart to use RRAM to do any training of the neural network because you have to change the width very frequently, but you have to do the verify, then it will take forever for the training. So you can do it for inference because you only train it and program it once. So here I emphasize that RRAM scaling lag behind compared to the SRAM. So the best available is 22 nanometer from TSMC and Intel. But here we believe this could be some sweet spot for some low-cost edge platform because for the edge device, you do not need advanced high-end, high-performance logic process. And from the cost perspective, 22 nanometer is very cheap for many of those, edge sensor or other, electronics that are not very high-end. So if you can enable some edge intelligence with RRAM at those technology nodes, this could be great. So here are some challenges we faced. So just to elaborate more. So we already see the ADC bottleneck in terms of area, taking too much area, and also the power consumption is high. So here the ADC requirement is unique. It does not require very high resolution, like 3 bit to 6 bit, less than 1 gigabit per second is good enough. But there is a stringent requirement on the area of the ADC. This is because if you look at the layout, let's say one column, you only have one T1R, and then you have a bunch of transistors here to form the ADC. So ideally, you need one ADC per column, every column. But here you can imagine you have dozens of transistors here. Here you only have one transistor. So it's impossible to have the column match, let's say one column, one ADC. Usually from the layout, you have one ADC shared with multiple columns by the mux. So this is not ideal because you can only turn on one column at one time. That means you have to spend more cycles if you operate, for example, 8 to 1 mux. You have to use 8 cycles to do the computation. So this is not ideal. So the stringent requirement on the area is the key challenge for ADC design. But ADC, you need thousands of transistors. So it's very difficult. So there are different kinds of ADC. So what we used earlier is flash ADC. It's very simple. You have some voltage mode sense amplifier, and then if you have 3 bits, you need 7, and then you have the follow-up encoder. So you do the comparison in parallel. You have the bit time voltage, then you compare with the sense together. And or you can use a SAR ADC. You can use only one sense, but you have to change the reference in multiple cycles. You use more latency, but then you can just use one comparator. So this is a SAR ADC. So as you can imagine, then the area-wise, of course, SAR ADC is more efficient as the resolution goes up, but you have to pay for more latency because you have to compare multiple cycles to determine the output. So here, the general recommendation is that for large partial sum, higher precision, we have to switch to SAR ADC, a 5-bit, 6-bit, because the power and area of flash ADC will exponentially explode. So this is not very sustainable for high precision. So for high precision, we have to switch to SAR ADC. Then we have to pay for a little bit of latency penalty. Then the challenge with the analog compute is always the noise and the variation. So here we show the write and verify, and we see a lot of tail bits. So here the process variation, not only from the RRAM programming, but also even intrinsically, for those peripheral circuits, ADC transistors, it will have the mismatch of the threshold voltage of those transistors. So the RRAM variation plus the peripheral circuits variation will basically become a very large challenge for the accuracy. So this is why we always see the degradation of the accuracy when we do this computation. So we could do some fine tuning. For example, the write and verify, and also ADC offset could be fine tuned with different, let's say, ADC references. But however, this is fine tuning is very costly. If you do the fine tuning for every ADC, you do not have enough resources to do that. So it's very challenging. And as the VDD and the temperature change, then when your references need to change as well. We did that through some dummy cells in the generation 1 chip, but still it's not perfect. So here we show that ADC output, you see a lot of variations along the ideal line. You have a lot of variations. So one idea is that we could retrain the neural network to accommodate the variation or offset. So that means the neural network model will be different for different chip. You need to fine tune the model a little bit to compensate for the variation for each chip. You could do this through the algorithm fine tuning. So with this fine tuning, we can recover some of the accuracy. So this is after your chip is fabricated, then you test the chip, and then you get some understanding about the offset of that chip, and then you redo the training of the algorithm a little bit, you fine tune a little bit, make the model unique to this individual chip. So still it's an overhead in the testing phase. And also we mentioned earlier the unstable resistance is pretty low, therefore the current is pretty large. Then this will cause the IR drop along the column. And also we have to use a large mux to basically transfer the current out. So here you see that the mux, this is from the Wenbang chip. Mux is much larger than the RRAM. And then the high voltage of RRAM programming, we need 3 volts. Then we need a lot of level shifter to generate the high voltage. So you see the area is not very efficient because of peripheral circuits, ADC, mux, level shifter take too much area compared to the RRAM. So this is not ideal. So here we basically summarize the challenges we face in the RRAM. I think some of the challenges could be addressed through the algorithm and circuit innovations, but some of the challenges are fundamental. For example, here the RRAM, if you cannot change the technology for the RRAM, the unstable will be low. And also the variations and noise are intrinsic with the mixed signal computation. So those are the fundamental challenges with the RRAM computing memory. So even though we demonstrated some prototype chip and we see other chips coming from other groups, but today there's no product yet because the reliability is still quite challenging. Okay, so here I just provide some references if you want to read more of our results. For example, the RRAM chip published in GSC, VLSI, SRP, CICC, and so on. And also here, this is a nice review article from the TCAS1 to just go over the RRAM-based computing memory. And also to IRPS paper about the reliability of the Wenbang chip, the multi-level RRAM and reliability. All right, I think that's all, and I'll be happy to take some questions. So we still have 20 minutes for our discussion.
谢谢于老师的介绍。那个同学们还是师长们，有没有一些问题想要跟于教授请教的？
对，我们可以用中文。有什么这个问题吗？
那个大家有没有问题想要跟于老师做一些请教的？就是说，如果说你们针对今天于老师的一些分享，或者说我知道有一些同学他们是自己有做这方面的设计的，那当然可能你们都还没有做这个 RRAM 的部分。那像有一些那个固态组的这个半导体组的老师，他们是有做一些 memory 的经验的，都欢迎大家一起交流。
于老师你好。
你好。
我想请教一下，因为你刚刚在 paper 里面有说一篇，取代 ADC 的设计就是用 first with 的方式。那请问，在未来就是可能边缘运算，像它对功耗的节省有很大的帮助，跟甚至是面积的使用率。那 你觉得未来用其他方式取代 ADC 会是一个趋势吗？还是说它
OK
算是一个分支这样？谢谢。
OK，这个是个好问题。是这样，就是在我们的这个 demonstration，有这个area power 有很大的改善，但是这个只是在2个就是我们这个 demonstration 你看到之前就是2个 array 之间的 communication。我觉得如果是取代这个 ADC 用这个 pulse width，is a good approach，但是这个也仅限于就是这个 inter array 在这个 adjacent array 之间。那比如说，我觉得可能 scalability 也许到4个 array，that's it，因为你这个at a certain point 还是需要 come back to digital，因为你这个 analog signal 你 keep propagating，那 eventually 你会 accumulate the error and noise。at some point 你要变回这个 digital，做一些这个error correction 啊，然后对一些 non-distance 的这个 communication，也是需要这个改回这个 digital。这 depends on 你这个 model 的 size， 如果是一些 edge 小的这个 application， 比如说 keyword spotting， 就是探测一些 keyword， 像你知道Hello Google、OK Siri 之类的。这些简单的 command， 如果它只是需要 detect 这些东西的话，对 edge 来说的话，这个kilobit 像我们这么大的这个2个 array 就足够了，其实是，这种情况下你可以 completely get rid of 这个ADC 2个 array 之间，但是如果你的 model size 很大，就是 megabit， 那你需要有7、8个这样的 array 或10几个这样的 array。那我觉得是很难，就是全部 propagate 整个 signal， 整个都是 analog domain， 从来不换成这个 digital， 10几个 array， 这个是很难的，在实际应用起来。所以 at certain point， 可能你还是需要把它换回这个 digital。这个是 case by case 的这个决定，就是对于什么样的 model， 什么样的 application， 在什么地方你要做这个 A to D 的转换。这个是需要这个 case by case 的这个去 study， 所以说，这个 analog 这个东西，scalability 是会有问题的，你小的东西，小的 scale 的也许可以，但是你做一个大的 system， 那是一定不行。所以在 at certain point， 我们还是要回到地上。
好，了解，谢谢老师。
这个维宇老师。我想请回到那个 Intel 跟 TSMC RRAM 的那一个表格，可以吗？
好。
对，这个表格我有一个问题是，我们可以看到说，在那个 reverse wide and speed 那个 row 的话，我们可以看到我们为什么在22奈米，它相较于 TSMC 40奈米制程下降的情况下，它的 voltage 却拉上去了？就是正常来讲，制程的 scale 越小的情况下 ，voltage 不是应该可以越来越低？然后还有它的脉宽为什么也需要更长？
首先这个 RRAM technology 它的这个 scaling， 它并不是 logic， 它不一定这个follow 这个 logic 的这个trend。最主要的原因是 different 的 foundry、different 的这个provider 他们这个不一样，所以你不能这个去直接这样比较。然后至于说这个 read voltage 这是个 design parameter， 然后至于说为什么 TSMC 这个和这个的区别，也许22纳米它 on-off ratio 更小，或它需要更大的这个 sensing time，所以它并不是完全的这个 follow 这个 logic 的这个 scaling 的 trend， 就是你得 case by case 的去看。
了解。那我还有一个问题是，如果到那个第二个，就是魏老师你第一个 case RRAM case 的 computing memory， 你有提到说是用3 bits 的 ADC， 那我想问一下就是相当多的那个可能 SCC 可能或是 JC 他们的 ADC 可能都是8 bit， 甚至有在更高的。那我想问一下魏老师设计3 bits 的原因是什么？
OK， 对，就是更高 bit 的 ADC，知道这个 overhead 很大，肯定是仨 ADC 要好一点。但是最关键的问题是因为我们 TSMC 刚才我不是说了，它的 on-off ratio 只有7倍，on-off ratio 只有7倍，那我们只能 enable 7个 row。那 enable 7个 row 的话，它的 full precision 就只有3 bit，所以你更高的precision ADC 没有意义，在我们这个 case。因为 on-off ratio 只有7倍，所以说你只能最多它让7个 row，7个 row 的话，你最多就只出3 bit 的 data。
了解，谢谢。
嗯哼，对，所以说如果你 technology 有比如说100倍，那你technology on-off ratio 100倍的话，那你可能就需要6个 bit ADC 了，或者7个 bit ADC 了。对，这 on-off ratio 都不大，你看这个 on-off ratio 都只有对小于10。
有，谢谢于老师。
还有没有同学还是老师们想要提出你们的想法？那我顺便请教于老师，就是说我们知道那个做 in-memory computing 啊，我们的 memory 它已经不是那么像 memory 了，因为毕竟它跟 logic combine 在一起了。那 logic 也不是那么像 logic 的，因为它每次都要去读取这个 memory 里面的 data，所以它的这个 scale， 一个是 scale， 它就好像不大可能再像以前 memory 做那么大了。啊，第二个是这个做 circuit 的部分的话，它的这个就是受限在这个 read out 的部分，所以它的 efficiency 好像还是会有一个限制所在。那不知道于老师针对这个部分有什么想法？
对，现在这些RRAM 或者是 MRAM 或者是其他的，这是 embedded memory。你看它这个 initial application 哈，对于这个 foundry 来说哈，它是做 e-flash replacement，它并不是做 computation。OK，像台积它offer 这个RRAM 或者 MRAM，它主要的customer 是比如说前段时间他们不是有新闻是 Infineon 跟台积不是签了一个很大的这个order，做 RRAM 的 microcontroller。所以它的主要是用于做这个 e-flash replacement 或者个 microcontroller 或者 automotive 车载的这些车上用的这些chip，所以这是他们的 initial target。你要把它改做这个 computation，所以需要有很多 challenge 需要 overcome。我刚才就提到，比如说这个，那它这个做 memory，它做 e-flash，它不需要这么多 level，而且它只需要2个 level，2个 level 它只需要这中间这个 gap 足够大就可以了。就是你能区别 on 和 off，因为中间你只要一个 reference， 不 cross 这个 reference 就好。但如果你是做 computation， 刚才我说的，就是不仅中间你这个要 gap 足够大，而且是每一个这个 distribution 你都要这个 tighten 到这个中间，所以这个要求是很高的。所以为什么这个现在还没有 product 放这个 RRAM 的这个computing memory， 虽然很多 research paper 啊我们也做，但是实际离这个 product 还很远，就是因为它的要求变了，它不是只是做 memory。所以为什么这些公司找我合作，像温邦、台积啊，他们也是希望让我们看一下，让我们学术界看一下，这做如果把它做 computation， 需要有解决哪些问题，或者这可行性有多少？
是的，是的。那因为于老师，你们主要就是不管是那个之后要帮我们分享的那个 FE-RAM， 或者是现在这个 RRAM， 它还有一个问题就是这个 integration。那 integration 在真的产品上的部分的话，它一个当然就是像你们在做的这个 3D 嘛。那除了 3D 以外，像我们自己在做这个in-memory computing， 即便我们是背上 SRAM 的它都还是会有，就是你 digital 的和这个 analog 的，必须要去做 integration，那它包括中间的 wire connection 啊什么的，那或者是这个 cosine 的部分啊，就会有一些新的 challenge 出来。那在 integration 这边，除了 3D 以外，于老师不知道还有没有一些新的想法？
对，这个 RRAM 呢，我们到时候 3D IC 的那个 lecture 会讲。对，有一个就是做 3D，然后你刚才提到的那个至于这个 design flow 的 challenge，这个是你做 SRAM 也是，你这个 mix signal flow 的话，一定你有这个 manual 的这部分，然后这个 digital 的部分，然后你中间是 integrate 之后你要做整个的full simulation，这个是这个EDA flow 上面是需要这个analog team 跟digital team 这个closely 这个 work together，但是是可以整个做 full simulation 的，你只要你把这个这些这个都 define 好，这个LVS 这些全部都弄好，然后做 整个 post real simulation，我没有自己做哈，都学生做的，那大概做整个的话是需要1-2天的这个 simulation，就整个 post layout simulation。
对，大概到这个几 K 的这个 scale 的话，大概你 posting 大概就是要跑个1-2天跑不掉。
是的，是的，是的，对。
所以
只能先每一个 block 先 verify，这个，然后一次性最后你只能对大概 check 一下，你不能 check 每个 case 来那个，这个很难。
确实。那有关这个还有一个 issue 就是那个 PVT 的 variation，就是像您这个 chip 的话是在40奈米，但是如果说更往下的话，它会变成是这个就已经不是传统的 CMOS 拉锯的部分。那部分的 PVT 就是不知道于老师这边的经验，它是比我们传统的 CMOS 来的更严重了，还是说其实还好？
我觉得 function 应该还好，你虽然理论上说是越 scale 这个 variability 会更大，但是他们 manage，因为他毕竟要 offer 这么多 customer，他一定是这个做了这个改进的，FinFET 你是想说 FinFET node，应该是还算 manageable，
OK， 收到。因为在台湾的话，我们现在学生们在学校里面其实还不是很容易有办法就是 SS 到 FinFET 的制程。那如果说大家在做 research， 比如说我们跟台大的这个计划在合作的话，我们是有机会去 SS 到，但是就是实际上大家经验还不像 CMOS 那么样的 solid。但是
对我也没有太多的经验，我们那个跟台积的16纳米和7纳米的这个 paperwork 也还在 lawyer 那里，他们律师还在还在谈，我们也没有这个就真的去这个就是 tape out 过16纳米，我们有16纳米 PDK 做一些 Monte Carlo simulation，但是还好，那至于做出来怎么样，我们没有经验也。
收到，但是他那个整个脚步应该会快一点的，因为他现在就是发现先前的部分，FinFET它是比较处于保护的状态。那现在其实他发现保护的大家其实这方面经验不够，反而对他来讲不是好事。所以他现在
对，台积它这个 FinFET University Program 不是刚刚这个开始嘛，所以跟几个学校，跟台湾的学校还有美国大概有那么几所就是合作的学校，包括我们，就是在搞这个对 paperwork。
OK， 那太好。就台湾这边大概是明年开始，就是今年大概也是在准备的阶段，明年开始会正式开始执行。
对，美国这边也差不多，我们一年这个律师好像都搞了好几个月了，我就在谈，对，有些反正一些 paperwork 啊，然后这个他们要什么，反正你知道，反正很多这些。
OK， 那不知道同学们、老师们还有没有一些问题想要跟于老师这边交流的？我们也许再开放一个问题，好不好？
那我有一个可能偏应用的问题想要请教老师。那像现在主流商用就是 commercial AI 运算的部分，主要都是用 NVIDIA 的显卡来做使用或training他们的 model。那像这种 CIM，它适用于哪一种应用呢？就是它跟 NVIDIA 这种 AI 运算，它主要的差异，因为像它这种是算 ASIC 的晶片，那它泛用性可能没有像 NVIDIA 他们 graphic card 那么高，那就是未来的发展就是会是融合在一起来说，就是会是不同的道路。
Okay, good question. 就 practical speaking， 这个 computing memory 像这种 approach，mixed 的这种 approach 是 scalability 是上不去，所以这个不会出现在 high performance computing 的 platform 里面。所以你的这个training 这些 large language model 或者什么的，你还得用3纳米、2纳米、1纳米的这个 high performance 的 CPU、GPU from 这些 major company 所以这个像RRAM 这种 computing memory 最可能合适的就是刚才我说的 edge inference，一些这些 low power 的这个 edge sensor 或者是什么的。比如说我跟 Google 有个 project，Google 他们想让我看，他们就是想做一个 edge inference， 就是在OK Google 这种，现在就是你知道这个 activate OK Google 之后，它送到这个data center 去做后面的 command 是什么，对吧？但如果你是把它做到 edge 的话，它这个 circuit 会 always on detection。always on detection 就 detect environmental 这个中间的这些比如说这些command， 它一旦这个activate 之后，然后后面它就要开始这个首先它 detect 到这个声音，然后它就要分析这个声音是什么，后面这个 inference chip 这个时候就是这个 RRAM 这种东西比较有用的地方了，因为你大部分时间你都是在 standby， 都是没有在运算，那你用其他 SRAM 或什么，你就会这个 consume 这个 leakage power。所以但是你一旦你 detect 到什么声音，你也需要立刻做出这个 decision， 对吧？那你如果是用 Flash 在 load 把 data 从 Flash load 到 SRAM 这个运算，那就很慢的。所以这种情况下 ，RRAM computing memory 就是一个好的 example。在这种情况下，但这个 market 很小啊，就是 compare to 你这个mainstream 的GPU 的这个 train 这个垃圾 model 这些所以说这个 market 是很不一样的。
好的，了解老师，所以它就是偏向边缘运算或者是mobile device 上的应用这样。
对，甚至是边缘的，甚至是这些 sensor node，一些 low cost 的一些 platform，low power，
好的，谢谢老师。
那个谢谢。那个还有没有同学有问题想要问的？如果大家没有问题，我们就再谢谢于老师，好不好？谢谢。
好，谢谢，这个时间比较晚，那我们下礼拜再。
对，就是下个礼拜于老师还会再帮我们分享新的议题，那大家就是要记得再把你的时间空下来。那我刚看大概我们今天上线有50几个师长和同仁还有同学，我们就下周再继续来听这个于老师跟大家的一些分享。谢谢于老师，谢谢大家。
谢谢，好，拜拜。
OK，拜拜。那还有一些同学，那个因为晚上比较忙，没有办法上线的，那我们之后都会有录影，所以大家可以回去再看影片。 谢谢。OK，拜拜。